Hello, everyone. Welcome to today's Fellowship of the Ring seminar. It's my pleasure to introduce the speaker. Alexandra Seceleanu will speak on reflection arrangements, Syzygies, and the containment problem.
Hello, thank you for having me speak here in this seminar. I'll start by echoing something that's been said before, which is it's really great to be able to welcome somebody into your house every Thursday in a safe way and have them present an interesting piece of mathematics. So thank you to all the previous speakers and the organizers for making that possible. And so in the first part of the talk today, I want to go over background that relates to essentially the three topics in the title of my talk. So to be more precise, in the first part of the talk, I will introduce reflection groups, invariant theory, and some ideas from subspace arrangements. And I mean, individually, these three are quite important areas of mathematics. So of course, I won't be able to say everything to give an exhaustive overview, but I'll focus mostly on the connections between these three areas. So starting with reflection groups, let me remind the definition of a reflection. So it's just a linear transformation that fixes a hyperplane, which is usually called a mirror or a reflecting hyperplane. So a reflection is just like a reflection in a mirror. And a reflection group is, for me, a finite group which can be generated by such reflections. You already see, in a way, the first connection to subspace arrangements in that any reflection group gives rise to a reflection hyperplane arrangement just by considering the set of all mirrors, so the set of all reflecting hyperplanes for all the reflections in the group. So I thought I would start by giving a few examples and maybe convincing you that we've all seen reflection groups before. So maybe the simplest example is the symmetric group. The symmetric group, as we all know, is generated by transpositions. But I want to think about the symmetric group really as being the group of n by n permutation matrices. So permutation matrix is just a matrix that has a single non-zero entry in every row and in every column, and that non-zero entry is a 1. So this set, of course, is a subgroup of the general linear group of n by n matrices over some field K. And so if we think about the linear transformation that corresponds to the transposition of I and j, then we see that it actually fixes the hyperplane that is the zero locus of xi minus xj, because really this transposition takes the equation xi minus xj to xj minus xi, but that is essentially, that is describing the same hyperplane. So this is the hyperplane fixed by the transposition ij. So this shows you that the symmetric group is really generated by reflections, and then also the reflection arrangement corresponding to the symmetric group consists of all these hyperplanes hij. So if I wanted to write down the equation defining this arrangement, then I would just take the product of all of these equations, xi minus xj. All right. So this is a reflection group that we all know and use probably a lot. I thought I would give another example of a more exotic reflection group. I'm going to call this generalized symmetric group, but it has an official name, which is called a monomial group. So sort of at a high level definition would be to say that this generalized symmetric group, which has a name, the name is GMMN, is the wreath product of the cyclic group of order M and the symmetric group of order N. But there's a very concrete definition that I actually want to use. So instead, I'm going to think about this group GMMN as a group of matrices. So it's going to be n by n permutation-like. Permutation-like matrices will mean here that there is a single non-zero entry in every row and in every column, but these non-zero entries are now not the number 1, but they are actually mth roots of 1. And also I want the determinant of these matrices to be equal to 1. I won't write down a specific example of such a matrix, but I will just observe that if we make m equals 1, then G11n is just our previous example, the symmetric group. So in this sense, these are generalized symmetric groups. Similar to what I said before, it turns out that you can write down a reflecting hyperplane, which is the zero locus of xi minus psi xj. Psi here is an mth root of 1. So these are the reflecting hyperplanes for certain elements of this group that resemble transpositions. And then the reflection arrangement corresponding to the group GMMN is described as the zero locus of, well, the product of all of these polynomials that I just wrote down. And this is a triple product, so it's indexed over I and j from 1 to n, but also over roots of unity. And if we group together and multiply, it's convenient to see that this can be rewritten as the product of xi to the m minus xj to the m over all I less than j. So even in some sense, the defining equation resembles the one for the symmetric group. It's just m power sub n. Okay. I wanted to show some pictures of what the arrangements for some monomial groups look like. So let me show you some pictures. So here are pictures of the reflection arrangements for the G223 and G333 groups. So G223 looks like a picture that any of us would have drawn in elementary geometry. It looks like the 3 sides of the triangle and maybe the 3 angle bisectors. But G333, it takes a while to wrap your mind around what is going on here. First of all, to define G333, we need cubic roots of unity, which are complex non-real numbers. So this picture naturally lives in the projective 2-plane over the complex numbers, and that means what are lines there cannot really be drawn as straight lines in my real picture here. But for example, this is a line or hyperplane in this arrangement, and this is another line in this arrangement. And there are, in fact, a total of 9 lines in this arrangement, and they meet, as you can sort of see here at a point, 3 lines meet. All right, so in some sense, it's a very highly symmetric hyperplane arrangement, and the symmetry is given exactly by the fact that it comes from a group that that actually even contains the symmetric group on 3 elements. All right, so regarding reflection groups, I wanted to mention a main central theorem in this area of investigation, which is a classification theorem for reflection groups produced by Shepard and Todd. So they showed that the irreducible complex reflection groups can be classified into one infinite family and this family contains a group called GMPN. So they are monomial groups. And the ones that I described just before were the case where M is equal to P. I won't describe this family in full generality. And then we have several sporadic groups. In fact, there are 34 such sporadic groups. And they are numbered G3 to G37 by Shepard and Todd. And they have ranks 2 to 8. So rank here means the dimension of the vector space that this group is acting on. All right, so some examples here. So as we have seen, the monomial groups, the infinite family, include such groups as the symmetric groups, but also the cyclic groups, the dihedral groups. So all the groups that we know and love from elementary group theory. And the sporadic ones include some very classical groups. So for example, they include the Weyl groups of the root systems E6, E7, and E8. So I will not use those, but I thought I would mention the connection here. So that's my little introduction to reflection groups and their arrangements. And so the next thing I want to talk about is invariant theory, very briefly. So of course, invariant theory is one of the parents of commutative algebra, if one can say so, going back to Hilbert and Noether and their goal to prove finite generation for various rings of invariance, which we are just about to define. So I will just look at invariant theory over a polynomial ring. So to do that, we'll take a subgroup of the general linear group of n by n matrices, and we're going to make it act on the polynomial ring. And perhaps what I wrote here is not extremely intuitive. More intuitive would be to say, well, this group G acts on the vector space spanned by the variables x1 through xn by the natural action as a subgroup of the general linear group. So that is what is written down right here. And then we can extend that action to polynomials by a group element acts on a polynomial simply by substituting each variable with the linear combination that results by the group action on the variables. All right. And so the way to make rings out of groups acting on other rings is to consider rings of invariance. So for example, the ring of invariance of this group G acting on the ring R is, well, the set of polynomials that are invariant under the action of every group element. So that's a very classical notion in ring theory. Let me say a little bit more here. So I want to mention the relationship between reflection groups and invariant theory. So actually, reflection groups can be characterized from the point of view of invariant theory. And the characterization is given by this famous theorem of Chevalley, Shepard, Todd, and Sayre. Which says that G is a reflection group. And let's take the characteristic of the field not dividing the order of G. So this is true if and only if the ring of invariance of the group acting on the polynomial ring is in turn a polynomial ring. Meaning that, this ring of invariance is a K algebra generated, say, by F1 through Fn, and F1 through Fn are algebraically independent.
Alex, you have a question in the chat.
Okay.
The question is, which of these reflection groups are symmetric? It's about the previous theorem.
Yeah, so in the Shepard-Todd classification, the G11N groups, so a subfamily of this infinite family, is the symmetric group. Yes, so they are a subfamily of this case. All right, so hopefully that answered that question. So let's actually go back and look at our examples from the perspective of invariant theory. So of course, probably this is well known to people. If we take the ring of invariance with respect to the action of the symmetric group, well, of course, this is generated by the elementary symmetric polynomials, right? But also by the power sums polynomials. So let me call those P1 through Pn. So Pi would be the sum of the ith powers of the variables, right? So that's one example. Let me do the G333 group also. So what kind of invariance does this monomial group have? Well, its ring of invariance turns out to be generated by XYZ, x cubed plus y cubed plus z cubed, and x to the 6 plus y to the 6 plus z to the 6. All right. And if you are a person who likes to be active during a talk, you might think that there's a criterion for polynomials to be algebraically independent. So the theorem here tells us that, for example, the polynomials listed here are algebraically independent. The criterion for that is that the determinant of their Jacobian matrix the Jacobian matrix has maximum rank. So if you like to be active, try to compute, and you don't know the answer yet, I suppose, try to compute the Jacobian of these three polynomials and see how it relates to the arrangement of this group. So something a little bit less classical that I will use is actually derivations and G-invariant derivations. So let's remember that the module of derivations of the polynomial ring R is the free R module generated by the partial derivatives. And so think about these partial derivatives as dual elements to the variables x1 through xn, because our group G acts on the vector space spanned by x1 through xn. It acts dually on the dual vector space spanned by the partial derivatives. And so it makes sense to talk about G, and that action is extended to this module of K derivation. So it makes sense to talk about the G-invariant derivations. And so this would be phi, a derivation of R, that has the property that G acting on phi is phi for all G in the group. So this is the RG module of G invariant K derivations on R. And for those who know about modules of logarithmic derivations and their relation to hyperplane arrangements, in fact, the module of logarithmic derivations can be obtained from this module of G-invariant derivation by extension of scalars from RG to R. I will not define what logarithmic derivations are in this talk, but it turns out that whether the module of logarithmic derivations is free as an R module is a very central theme in hyperplane arrangement theory. So because this module is very closely related, it makes sense to ask about whether the module of G-invariant derivations is free. And in fact, the answer is yes. So there is a theorem that tells us that if G is a reflection group, if G is a reflection group, then the module of G-invariant K derivation is free of the same rank as the group G. All right, and actually, from this theorem, you can immediately deduce by extension of scalars that reflection arrangements are free in the sense of having free modules of logarithmic derivations. All right, so this is generalities about invariant theory and its relation to reflection groups. And then I thought I would list a few major problems in invariant theory. Some of these are extremely classical. So for example, finding generators and relations for rings of invariants is an extremely classical problem. Fortunately, in many cases, it has been solved. So for example, for reflection groups, the generators of the ring of invariants have been determined, and we're actually going to use that later on. For other groups, or when it's not possible to find these exactly, of course, it's interesting to find bounds on the degrees of the generators or relations. And then I just threw this last one in there because we just talked about the G-invariant derivations. I don't think they are studied as much, but of course the same questions would be interesting for this module. Okay, so we're gonna switch gear now to subspace arrangements for a little bit. So let's head over there. Okay. So we've already seen hyperplane arrangements in the previous sections. Subspace arrangements are a generalization, let's say, of a hyperplane arrangement, in that a subspace arrangement is a union of linear subspaces of affine or projective space. These subspaces are not necessarily of codimension 1, so they're not necessarily hyperplanes anymore. They can have arbitrary codimension, and the only restriction I'm going to impose is that there are no containments between these subspaces. And so if this is a subspace arrangement X written as a union of linear spaces, then of course the defining ideal of X will be the intersection of the defining ideal of ideals of the various subspaces. So already one can ask several questions about ideals defining subspace arrangements. What are their generators? What is their Hilbert function? What are the homological invariants of these ideals, like projective dimension or regularity, or maybe we can say what the Betty numbers are. I will, there are many results in this direction. I will just give one that I like. So here's a theorem by Harm Dirksen and Jessica Sidman that says that if X is an arrangement of D subspaces, so linear subspaces, then the regularity, Kastamova-Mumford regularity of the ideal defining this arrangement is at most D. Maybe it's less or equal. But the one thing I want to point out about this theorem, as I understand it, its origins are motivated by trying to bound degrees of generators for certain rings of invariants. So there are obvious connections, or maybe not obvious, but there are deep connections between invariant theory and subspace arrangement theory. In this talk, I will look at certain special types of subspace arrangements. So let's define something that I will call the codimension C truncation of a hyperplane arrangement. Is, well, it'll be the set of intersections of C linearly independent hyperplanes in the arrangement. So I feel like this truncation idea is a term that appears more often in hyperplane arrangement theory than in commutative algebra. Nevertheless, let's think about the case C equal 2. So what is the codimension 2 truncation? Is just the intersection of pairs of hyperplanes in our arrangement. Well, that actually, from an algebraic or geometric perspective, is just the singular locus of a hyperplane arrangement. So that's the codimension 2 truncation. And the codimension 3 truncation would capture the singularities of the singular locus and so on. But really, I'm just in the second part going to focus on the codimension 2 truncation, which is the singular locus of a hyperplane arrangement. And let me give one more definition. I will define a fattening, so not to be rude to hyperplane arrangements, but I will define the nth fattening of actually a subspace arrangement. X to be the scheme defined by this ideal that I will call, well, this is the m symbolic power of the ideal defining X, but in this case, it has a very concrete definition. It's the intersection of the mth powers of the components, of the ideals defining the components in my arrangement. So that is the mth fattening of a subspace arrangement. And one can ask really the same questions that we asked here about subspace arrangements. One can ask about their fattening. So what are the generators? What are the homological invariants? Unfortunately, I mean, we don't have an all-encompassing theorem that applies to every fattening of every subspace arrangement. So we don't have something as general as this theorem here. But we have some information. So for example, if X is a union of all the codimension C coordinate subspaces. So in my previous terminology, this would be the codimension C truncation of the arrangement of coordinate hyperplanes. Then we know the Betty numbers for, well, sort of know, but information about the Betty numbers of the mth fattenings can be found in a paper by John Bierman, Adnan de Alba, Federico Galletto, Satoshi Murai, Uwe Nagel, Tim Römer, Tina O'Keefe, and myself. This example is an example of a truncation of a hyperplane arrangement where the hyperplanes intersect in a way very much transversally. So a generalization of that idea is called a star configuration. And So it turns out that the Betty numbers of star configurations, even the fattenings, they reduce in some sense to monomial ideals. So they reduce to the previous case, and this is by work of Tony Jeremita and Juan Migliore, and oh, sorry, I forgot Brian Harborn and Juan Migliore and even Novel. And then one can generalize this generalization even further and go far away from looking at arrangements of, or truncations of hyperplane arrangements and kind of do truncations of arrangements of hypersurfaces. And so some of those are called star configurations of hypersurfaces. And so the Betty numbers for those are analyzed in a paper by Paulo Montero. And of course, there's much more in all of these works. I'm just focusing on Betty numbers for concreteness for now. So let me, I think I'm about to sort of close the first half by just adding one more problem to our problem list. So that will be the problem that I will mostly focus on in the second part. And that is the containment problem. So I'll just phrase it for subspace arrangements for concreteness, but it can be phrased for any ideal in a regular ring or even in arbitrary rings. And it says, okay, so for which pairs, called the pairs, pairs of positive integers, R and M, for which pairs do we have a containment of the ideal defining the mth fattening of my subspace arrangement inside the rth power of the ideal defining the arrangement? So, so one reason this problem, there are several reasons why this problem is interesting, but maybe I will just list two of them. So one reason is that one wants to get some sort of an algebraic handle on well, on these fattenings, and for example, get a handle or get an approximate idea of their generators. And so containments of this type allow us to get a handle on these ideals, defining fattenings via ideals that are a priori much more simple to handle algebraically, which are the ordinary powers of this ideal defining the subspace arrangement. Like another reason to do this comparison is because it can be viewed as a comparison of topologies. The ordinary powers of an ideal define a topology, the symbolic powers of an ideal, which are just these fattening ideals that I define another topology. And this is the way to estimate or compare the two. So I think that is all I wanted to say by way of introduction to these three areas. And if there are questions, I'm happy to answer, but this, I think, would be a time for a break.
Are there any questions? We don't have any questions in the chat, so let's take a 5-minute break.
I was too slow on the unmuting to ask my question, but I wondered whether there's substantially more known in this special case than in the general symbolic powers containment case.
So sorry, I couldn't quite.
People ask the same containment question about symbolic powers, and I'm sure you know this extensive literature. Craig and his students and many other people. But is there a lot more known in the arrangements case? It seems like a much easier question. Or
yeah, so actually most of what is known is an easier, well, a good deal of what is known can be phrased in terms of arrangements. So I'll say a little bit about that in the second part, but I mean, okay, that's probably an exaggeration, but anyways, I feel like we have, as your intuition might tell you, we have a better chance of solving this kind of problems for subspace arrangements. So that's an area where a lot of effort has gone into that, and we're still working on it, but more is known there, I feel like, than in the general case.
Good start anyway. Lots of interesting mathematics mentioned. I always heard the Shepard-Todd theorem stated in terms of pseudo-reflections instead of...
Yeah, so that's the correct terminology, but I think that would have lengthened my talk by a minute, so I dropped the word pseudo.
I see. So you include that case?
Yes.
Yes, yeah.
Somebody is commenting in the chat that Shepard and Todd themselves called what we call now pseudo-reflection groups, they called reflection groups in their original paper, but
I guess it's time to start the second part of the talk.
Okay, so I'll start the second part of the talk by mentioning that this is joint work with Van Drapkin. And it's on the archive. It's been there for a few months now. I'll start with the 10-second summary of this part of the talk, or the takeaway, in case I don't get this across clearly by the end. The takeaway is that we're going to look at an instance of this containment problem, and the main idea is that this containment problem will be reflected in the structure of the syzygies of certain ideals. And these syzygies, in turn, will be determined by reflection groups, actually invariants of certain reflection groups. So the takeaway of this talk is that there are interrelations between these three notions: containment problem, syzygies, and invariants of reflection groups. And that's what I hope to stress in this part of the talk. So just as a reminder, because this is already on the previous page, what is the containment problem again? So I believe Eloisa spoke about this in full generality in the seminar, but for the purpose of this talk, I am just restricting to subspace arrangements and asking, for each positive integer R and M, is the M symbolic power of the ideal defining a subspace arrangement contained in the Rth ordinary path? And so there's a far-reaching and very general answer to the more general containment problem, and that's given by a theorem by Lorenzine, Laurel Lazarsfeld, and Karen Smith, and also separately by Mel Hoster and Craig Hunicke, and also more recently by Lintron Ma and Carl Schweid. Okay, so I will just again, for simplicity, the theorem is more general, but I will phrase it like this. So if I is an equidimensional ideal in a regular ring with height of I equals to C, then the C times R symbolic power of I is contained in the rth ordinary power, and this applies uniformly for any exponent R. And so in some sense, this covers many cases of pairs in the containment problem. But the natural question is, are there any pairs that are not covered by this broad theorem? And essentially, I want to single out the case in which this theorem is tight by saying that the ideal I is containment tight if we cannot improve this containment. So I to the symbolic power CR minus 1 is actually not contained in I to the R for some R. Right? So for some R I cannot improve this theorem, then I will call the ideal containment type. That's a term that we made up to ease discussion here. So let me give an example of such a containment tight ideal. This is currently a fairly famous example that was discovered by Dunitsky, Schoenberg, and Hashka Tutay-Gajinska. Oops. So if you recall, and even if you don't recall, this is the reflection arrangement of the group G333. And I will take X to be the singular locus of this arrangement. Or if you want the codimension 2 truncation of this arrangement. In any case, X itself, if you think about it, is a subspace arrangement. It's actually a set of points, but it is a subspace arrangement. And then it turns out, so C, the codimension is 2. And then it turns out that, well, the theorem predicts, and of course it is true, that the fourth symbolic power of the ideal defining X is contained in the second ordinary power, but one can verify that the third symbolic power is not contained in the second ordinary power. So in our terminology above, the ideal, these 12 points that are marked in various colors in the picture is containment. Okay, so this is sort of the example that started a long line of inquiry into properties of similar configurations. So our problem that we are going to address in this talk is, well, let's try to push this idea and see which reflection arrangements have containment tight singular loci. Okay. So we are, in brief, studying an instance of the containment problem for subspace arrangements, which are codimension 2 truncations of reflection hyperplane arrangements. All right. So, so now I will say what we know about this question. Before I do that, it might be good to establish some notation. So let's do that. So I want to refer by J of G rather to the ideal defining the singular locus of a reflection arrangement A of G. So that's the reflection arrangement of the reflection group G. Okay. And so I want to study the containment problem for these ideals J of G. Sorry for the switch in notation. We've switched from I of X to J of G. So if you want, well, if you're an algebraist and you want to study an ideal, it's kind of unsettling not to know its generators. So first of all, I will say something about generators and actually syzygies for these ideals J of G. So ideals defining singular loci of reflection arrangements. Okay, so let me cycle back to the exercise I mentioned in the previous part of the talk. So what happens if we take the Jacobian matrix of a set of generators for the ring of invariants of a reflection group? So here's the solution to that exercise. It's actually a theorem. So let's say G is a reflection group. And its ring of invariants, RG, is generated by the primary invariants or basic invariants F1 through Fn. Then actually, if you take the determinant of this matrix of partial derivatives, so partial Fj, partial Xi, what you're going to get is you're going to get the product of the linear forms defining the various hyperplanes in the arrangement. So let's say the product over H, a hyperplane in the arrangement corresponding to G, L sub H will be the linear form determining H. And then this is almost true, but not exactly. Then we have an exponent. So the exponent is actually the order of the reflection G whose reflecting hyperplane is H. So why do I bring this up? Because if you sort of ignore this exponent for a second, then this determinant gives you the defining equation of the arrangement. And if you're willing to apply radicals to the ideal generated by this determinant actually gives us the defining equation of the arrangement up to radical. Okay, so this is a very, I think, well-known result. Let me maybe illustrate it by one very quick example to make sure we are on board. So, you know,
we have 2 questions in the chat.
Okay, I can see the questions. So, so the answer to the first question is, I suppose the question is about this example right here. whether the fifth symbolic power is inside the third ordinary, and the answer is yes. And the second question is, these invariants might not be unique, and the answer is yes, they might not be unique. And that doesn't make a difference. So for my example, I'm going to take the power sums as the basic invariants for the symmetric group, and take the Jacobian determinant of the power sums. What is it? Well, it's the determinant of this matrix. So this was the exercise, if you want. You can see very well that this is the Vandermonde determinant. So it gives you, in this case, exactly the defining equation of the arrangement. All right. So the theorem is a generalization of this fact. So now, what I'm going to say next is I want to find equations for this ideal J of G. So not the arrangement itself, but the defining equations for its singular locus. And the theorem about those equations is also given in terms of minors of certain matrices of partial derivatives. So let me jump to that theorem. This is the first theorem. So J is always a reflection group throughout this part of the talk. Then here's what we can say about the ideal that defines the singular locus of the reflection arrangement of G. Actually, I forgot to write this down, but this ideal is in fact perfect and height 2. That's not a given because, for example, there are configurations of lines in P3 that are not defined by perfect ideals. So this actually, the statement has some content. But perhaps more interestingly, we can describe the generators of this ideal as either the maximal minor of a Jacobian matrix of a set of basic invariants for the group. So they're precisely the lowest degree basic invariants, or the coefficient matrix, I will explain what that means, of a set of basic derivations of lowest degrees. So what I want to say is, in some sense, our theorem here, you can say, looks like the previous theorem, but uses fewer basic invariants. And so you get, instead of an n by n matrix, you get an n by n minus 1 matrix. And so you're taking the maximal minors of that matrix. I find it best to explain this by means of an example. So here's an example of case 1.
There is a new question about the theorem.
Is the reflection,
whether the reflection group is irreducible?
Yes, I believe, let's put that in there, thank you. And complex, by the way. So let me give an example of case 1 where the ideal is generated by the minors of basic invariants. So we'll look at the example that I gave here and this ideal that I was talking about. So for J of G333. Actually, if we look at the partials of the lowest 2 degree invariants, those were X, Y, Z, and x cubed plus y cubed plus z cubed, right? So we have to take the gradients of these two, and we get yz, xz, and xy, and x squared, y squared, and z squared. And it turns out that this ideal is generated by the 2 by 2 minors of that matrix. This is an example of case 1. I'm not going to give precisely an example of case 2, but I'm going to give a remark on case 2. So the remark is, in fact, there is this one distinguished derivation called the Euler derivation. And the Euler derivation is always the lowest degree generator of the module of G invariant derivations. So let's call this delta upper E for Euler. So it looks like x1 partial x1 plus dot 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 xn partial xn. So this is always a basic derivation. So this means a generator for the module of G invariant derivations. And so this means if my ideal is in case 2, so if J of G is in case 2, then the coefficients of this Euler derivation, which are x1 through xn, appear as, this is what case 2 is saying really, they appear as a column in the Hilbert-Birch matrix of this ideal J of G. So it has, J of G has a linear syzygy. And that linear syzygy is given by this column x1 through x. So another way, which I should have probably mentioned, of interpreting this theorem is that it describes the Hilbert-Birch matrix for these ideals J of G. The Hilbert-Birch matrix is obtained by taking partial derivatives of the invariant polynomials or by taking coefficients of the invariant derivation. All right. So now, because we know the Hilbert-Birch matrix and we know that the ideal J of G is perfect, this actually determines, this theorem determines at the same time the generators and all the syzygies of, for this family of ideals. So the next thing I want to say is how this affects the containment problem. So as you can see here, there's a dichotomy in this theorem, 1 and 2 cases. Case 1, as I showed in the example here, corresponds to something that I explained was a containment tight ideal. So we will see that essentially this dichotomy persists in the next theorem, which talks about containments, in that whenever our ideal is in case 1, then there will be some sort of containment tightness. And whenever the ideal will be in case 2, there will not be containment tightness. So that's pretty vague. So let me say something. Oh, sorry, I see a question in the chat. So let me maybe process this question. Is there any relation between the degree of LH and its, so LH is a linear polynomial, it's degree 1. no matter what exponent it has. So no relation there, and a degree of LH is 1. Okay, so let me move on to containment. So I was saying, just keep in mind this dichotomy in the first theorem. So here's a theorem about containment. So we're looking again at the family of ideals defining singular loci of reflection rather reflection arrangements. Okay, so we can say something about the containments of the third symbolic power in the second ordinary power. So this would be the case if you want the case R equals 2, and we are for the rest of the talk in codimension 2. Okay, so so this containment holds if and only if no irreducible factor of G is in that list of groups given here. So I don't expect this groups to be close friends to anybody, but let me just say a few words about them. So obviously, this is some sort of a classification theorem because we have Shepard and Todd classification theorem for irreducible reflection groups. Most theorems that have to do with reflection groups classify them in some way or another. And so our theorem here is also a classification theorem. One way to process this theorem is to say that each of these groups here gives rise to a containment tight ideal. In fact, the fact that these two groups and the G33N, so this is n equals 3 case, gave rise to containment tight ideals, these ones were previously known. But the 3 ones in here, and the case of m greater than 3 in the infinite family, these are new examples. So these are new examples of containment tight ideals. They have the notable feature that they arise in higher dimensional ambient spaces than the examples that were previously known. So they're respectively arrangements in P4, P5, P6, and then Pn minus 1 for arbitrary n. Actually, sorry, these are not containment tight, but they're new examples of this phenomenon of non-containment. Okay, so we're not doing super great on time, so maybe I will say just a couple of words about what goes into this theorem. So, so there are 2 crucial ingredients, which is a reduction to, let's say, low embedding dimension. So I really like this lemma. So this was Ben's idea. So let's call it Ben's lemma. It turns out that to check a containment of the m symbolic power of the ideal J of G in the rth ordinary power, it suffices to check the same containment but for G replaced with H, where H is a subgroup of G. It turns out that subgroups of reflection groups are themselves reflection groups. That's a theorem. It's not obvious. With rank of G, with the rank of H, so that's like the embedding dimension of the arrangement of H, less or equal to the big height of J, G to the R. Okay, so the big height is the largest height of an associated prime, but actually this turns out to be bounded by R plus 1. So if R is really small, namely 2 in the theorem here, this lemma is a reduction to embedding dimension 3. Okay, so that's why we can do the R equals 2 case. This is why, and another thing. The other thing is that we have good Syzygies criteria. In embedding dimension 3. So I really like this theorem. So this is a theorem by Eloisa Grifo and Craig Hunicke and Vivek Mukunda, and that makes life quite easy sometimes. So it says, if I have an ideal J in a polynomial ring in 3 variables, not in characteristic 3, and J is perfect, codimension 2, then if you consider the ideal of entries of the Hilbert-Bridge matrix of J, and if that can be generated by at most 5 elements, then this actually implies that that the symbolic cube of J is contained in the ordinary square. So you can read containments off of Syzygies. Now the previous theorem actually tells us in case 2, where one of the Syzygies comes from the Euler derivation, that this ideal here is actually the maximal ideal. Well, of course, the maximal ideal in embedding dimension 3 is generated by much fewer than 5 elements, right? So in case 2, this theorem, together with reduction to low embedding dimension, does the trick. And then in case 1, it turns out that, well, all of these other groups belong to case 1. All right. So let me take one breath and check the chat. So somebody asks, should H be irreducible? Here you can take H to be irreducible. That's correct. And in fact, you can sort of, as a preliminary step, reduce to G being irreducible. I will skip that because we're close on time. But that's not a huge problem. And then somebody asked why characteristic not equal to 3. It's because the proof breaks down in characteristic 3. It's all I'm gonna say. I'm not actually sure that we have examples that this condition is needed. Somebody can correct me in the chat if I'm wrong about that. But just the proof does not work. Right. So in the last few minutes, so I'm going to talk about what is probably the obvious question is, okay, we can say we can write down a classification of our reflection groups in terms of whether this specific, very specific containment, so the symbolic cube in the ordinary square, happens or not. And that classification happens to coincide with a classification of the generators and Syzygies of Hilbert-Birch matrices of the corresponding ideal. But how about higher exponents than r equals to 2? The problem with that is, of course, the reduction to low embedding dimension is not so good anymore. The embedding dimension is not so low. Also, we do not have Syzygy criteria in. We do have some criteria, but they're not nearly as effective in higher embedding dimension. Nevertheless, we can say a few things. So I will end with what we, I guess nowadays call the stable containment problem. So based on some pretty solid evidence, there's a conjecture that has started being known as the stable Harborn conjecture, which says that for ideals that are radical and equidimensional of codimension C, one should be able to actually have containments that are improved from the theorem that I presented before. The theorem had the containment of j to the symbolic CR in j to the ordinary R. This improves by diminishing the exponent on the symbolic power by C minus 1. But at the expense of requiring the ordinary exponent just to be large enough. So this conjecture, if we were to put for any R here, then the examples that I talked about before would all be counterexamples to this conjecture, but all known counterexamples have this feature that they have R equals to 2. So now the conjecture is in a way asymptotic. Okay, so once again, I'm just going to talk about the case of codimension or height 2. So the stable Harborn conjecture here is that j to the 2r minus 1 symbolic power is contained in j to the rth ordinary power for r large enough. So what can we say about this? Well, we can hope to verify it in the case where J defines the singular locus of a reflection arrangement, and we almost do. So our last theorem is that we can verify this conjecture in that setting, but assuming that the embedding dimension is assuming that, I should say, the irreducible factors of this group G have rank at most 3. So somehow the irreducible factors are in low embedding dimension. If we assume that, then actually this stable Harborn conjecture holds. So this includes, this includes all the examples. Sorry, let me go back. This includes all the J of G's for the groups G circled in red here. So let me make a note of that. So although the containment of the third symbolic power in the second ordinary power fails for the group circled in red, the stable containment holds. We don't know much, we don't know anything beyond third symbolic power and second ordinary power for the groups circled in blue, especially for the sporadic ones. So maybe I will end with what has already perhaps been asked in in the chat, which is this question. So for the higher dimensional, let's say, for G of rank bigger than 3, that's what I should say, does the stable containment conjecture hold for this ideal J of G defining the singular locus? In particular, we don't even know if the case R equals 3 works out. So if the fifth symbolic power is contained in the third ordinary power. The reason we don't know is we don't, well, we know the Syzygies, but it's harder to produce effective criteria for containments in higher embedding dimension. Okay, so I think that's all I had to say. Thanks for your attention. I do see there is another question in the chat. So in theorem C, is it a tight containment? Yes, so right, so whenever this containment doesn't hold, for one R, we would say that J of G is containment tight. But, you know, if it, okay, so let me backtrack. So even those ideals that are containment tight, by failing this containment for R equals to 2, they still satisfy the stable Harbon conjecture. That's the content of theorem C, I guess. Sorry, hopefully that answers your question. So Francesca asks about the classification from here into case 1 and case 2 and how, yeah, so actually, yes, I was right, actually. Case 1 does produce containment tight ideals. So all that is in red and in blue is containment tight because of the non-containment of the third symbolic power into the second ordinary power. It's just that we don't know, actually, some of the ones that, you know, that have containment of the third symbolic into the second ordinary might be containment tight because of other exponents. But yes, so case 1 already gives us examples of containment tight ideals. Case 2, we do not know. Connection to linear Syzygies, yes. Case 2 has linear Syzygies. Actually, it has the variables as one linear Syzygy. Now, that makes it very, very easy to apply this specific Syzygy criterion. So in some sense, I mean, in some sense, I have a feeling that having low degree Syzygies helps produce enhanced containments. Of course, that's a feeling and not a mathematical statement, but here is a mathematical statement that you can make out of this theorem, is that if you have a linear Syzygy, well, if that linear Syzygy happens to be given by 3 linearly independent forms, then you have this specific containment. So I think there's some connection, more general, but does the proof about the generators of J of G use the Shepard-Todd? Yes, it does use the Shepard-Todd classification.
It seems there are no more questions. Let's thank Alexandra for a great talk.